Very good morning, everyone. And today we are going to discuss on a very important topic from Design and Analysis of Algorithms course, which is binomial heap. Myself is Dr. Anju Mishra, and I'm Associate Professor in the Department of Information Technology in Akgec Engineering College. So, first of all, today's objectives are to understand the concept of binomial heap and what associated operations are available for us to manipulate the binomial heap data structure. Second, we have to see that what is the time complexity of these operations. And in today's lecture, I'm going to especially cover up on the introduction of the binomial heaps and one important operation which is called as the union or the merging of the binomial heap. So first of all, we need to know that what the binomial heap data structure is, and since we already have discussed over the heap data structure, in a heap data structure, we know that there are two types of heap data structures that we can create. One version is called as the minimum heap data structure. So in the min heap data structure, the value of the parent node should always be lesser than or equal to the children of this node. So that is one of the important property of the minimum heap. Similarly, we can create a heap data structure which satisfies the max heap property, and in the max heap property, the value of the parent node should always be greater than or equal to its children nodes. So when I talk about the minimum heap or the maximum heap, recursively the same definition applies to all the levels of the tree data structures, and that way the heap is going to be created. Now, when we talk about a minimum heap or a maximum heap, we are mostly talking about a binary heap data structure. So binary heap is the data structure that we already have discussed when we have taken up for example, the heap sort algorithms for sorting n number of elements. So binary heap we already have gone through, and now we are going to discuss over the binomial heap. So the first thing that we need to know about binomial heap is that binomial heap specifically is an extension of these binary heap data structures. Since binary heap can only contain at most two child nodes from a specific node in the tree data structures, thereby we say that it is a binary heap. But in binomial heap, we can have multiple children emerging out of a specific node. Now there are certain properties of the binomial heap. For example, a binomial heap is essentially a collection of binomial trees. So binomial tree is the building blocks of creating a binomial heap data structures, and how to create these binomial trees that we will be discussing in a moment. The second property is that each binomial tree satisfies the min heap property. So to create a binomial tree, first of all, we need to keep in mind that the tree should be a minimum heap data structure. Now, binomial heap is used to implement a priority queue. So this is the application of this data structure, that for implementing the priority queues, we are mostly using the binomial heaps. And we already have discussed that it is essentially a extension of the binary heap, and it provides for faster merge and union operations. So for example, if multiple heap trees we have with us, we can combine them together easily and with faster operational speed in case of binomial heaps. So first of all, let us take the topic of the binomial tree, that what is a binomial tree and how to create binomial trees, and then the rest of the part will be discussing on how to merge or how to combine these binomial trees to form a binomial heap. So binomial tree is basically a kind of ordered tree which is defined recursively, and most of the time we are writing or we are specifying a binomial tree as bk. Now this subscript k refers to here as the degree of the binomial tree. So now k represents the degree of the binomial tree. Now, if I have written BK, this BK refers to a binomial tree where the order of the binomial tree is K. Now, for example, a binomial tree BK, for example, if we keep the value of K is equal to 0, we can write this binomial tree, or we can represent this binomial tree as B naught. So, B naught essentially is a binomial tree which is having a degree of 0. And if I talk about the total number of nodes in a binomial tree, how I can find it out? So, the total number of nodes in a binomial tree are always 2 raised to the power K. Right. So, for example, if the value of K is 0, or if we are talking about binomial tree with degree 0, we can see that the total number of nodes will be equal to 2 raised to the power 0. So, this is the total number of nodes will be equal to 2 raised to the power 0, and 2 raised to the power 0 means 1. So, basically B naught always has a single node only. Now, the same concept can be recursively applied, and we will be able to find out the number of nodes in a binomial tree with higher degree. So, for example, if I keep the degree of the binomial tree as 1, so I am keeping K is equal to 1, then in that case the total number of nodes can be calculated as 2 raised to the power 1, and this comes to 2. So, when we are referring to B1, which is a binomial tree of degree 1, the total number of nodes needs to be 2, right? Similar ways, for example, I need to create, or I am having a binomial tree with degree 2. Now, the total number of nodes here will be equal to 2 raised to the power 2, which will evaluate to 4. So, this way, the same formula we will apply to find out the total number of nodes from a binomial tree. And as you can see that if we talk about BK, the total number of nodes in BK will be equals to 2 raised to the power K. So, this is the way how we can calculate the total number of nodes in a binomial tree with a certain degree. And after this, one more important property of a binomial tree is that how to create a binomial tree. So, for creation, what we need to do, that first of all we need to know about the degree of the binomial tree that we want to create. So, for example, if I want to create a binomial tree with degree BK, how I'm going to create this binomial tree with K degree? So, for this I need to take two binomial trees with degree BK minus 1, and I'm joining them together by making one tree as the left child of the another binomial tree. So, this way I can create a binomial tree of higher degree. So, for example, if I need to create a binomial tree with degree, for example, 1. So, to create B1, what I need to do? So, with this property, how we are going to create a binomial tree with degree 1? So, for this I need two binomial trees with degree 0. So, for example, this is the first and this is the second binomial tree with the degree 0. So, I have taken these two. How I am going to represent these binomial trees? So, we all know that in binomial tree with degree 0, we are having only a single node. So, this B naught represent a single node. I am shading it, and this B naught again having a single node. Now, we need to combine these two to form this B1. So, we are combining B naught and B naught together to find out or to create another binomial tree with degree 1, right? Now, how we are going to merge these two binomial trees with degree 0? So, for that we already have seen that we just need to make the one binomial tree as the left child of the other binomial tree, and that way the binomial tree with degree 1 will be created. So, in this case, for example, I can take one B naught and the other B naught I am associating as the left child of this previous B naught. So, that way now this tree represents a binomial tree with degree 1. Recursively, we can create binomial trees with higher degrees. So, for example, Now I want to create a binomial tree, for example, of degree 2. So to create a B2 like this, what I need to do? I need two binomial trees with degree 1. So this is the binomial tree with degree 1. I need to take two components like this. For example, this is the first component and this is the second component that I have with me. Now I need to just join them. Here plus is not an arithmetic operator, rather it is utilized here to show the union or the join operation performed over the binomial trees. This tree is having degree 1 and this tree again having degree 1. Now how we are going to create a binomial heap of degree 2, just by connecting these two and making one the left child of the other. So this is the way how we are creating. So this is the subtree that we have attached as a left child of the another binomial tree. So now this whole component here represent a binomial tree with degree 2. You can see this is the structure that we are getting. Similar ways, recursively, we will be able to create the binomial trees with higher degrees. So I already have shown here one of the binomial tree with degree 3. So how this degree 3 binomial tree is going to be created? We have taken two components or two binomial trees with degree 2 and this is another one with degree 2, and we are combining them or joining them together by making one as the left child of the other one. So that way we are getting a binomial tree of higher degree, right? Now, another property that we can see from here is that if you focus on this particular, figure, what I can observe here, that the root node, which is this here, this is the root of this binomial tree with degree B3, right? Now, this root node is attached to certain binomial trees here. So now, for example, if I, let us take the child subtrees of this root node, they are having a specific property. So for example, if I start from the right hand side and I move towards the left hand side, I can see that the first component here, okay, so this subtree is actually a binomial tree with degree B0, okay, and this subtree again, this is a binomial tree with degree 1, right? And the third component or the third subtree here, as we can see that this is a binomial tree of degree 2. So in a binomial tree, when we are moving from right to left or from left to right, whatever the convention we are using, we will be getting binomial trees in an ordered manner, ordered based on the degree of the binomial tree. So as you can see here, that first we are having a component B0, then we are having another component B1, then we are having the third component, which is B2. So B3 is essentially containing here B0, B1 and one subtree with degree B2. So this is again a important property of the binomial trees. If I want to generalize this thing, I can see that if this is the root node with degree k, I will be having a tree B0 here, then another tree, like for example, which is having a degree 1, then I will be having another such tree having degree 1 higher than the previous one, and this way it will be continued to have the tree with degree B k minus 2, and similar ways the last subtree here will be having a degree k minus 1. So in degree k binomial tree, we will be having all such components which are connected together, and they are connected in an ordered fashion. So that way we say that binomial trees are ordered trees. Now let us come to the point of creating binomial heap. So for example, if I want to create a binomial heap with n nodes, the binomial heap should satisfy these two properties. So the first property says that every binomial tree, we already know that binomial heap is created by collecting together the binomial trees, and The first property of binomial heap says that every such binomial tree in the heap data structure must satisfy the minimum heap property. So every individual tree, B0, B1, B2, those binomial trees, they must essentially be the minimum heaps in themselves. The second property that we have with us, or that the heap needs to follow, is that for any non-negative integer k, there should be at least one binomial tree in the heap where root has degree k. So what does this second property means? So this essentially means that in a binary heap, a binomial tree with a specific degree can occur with a frequency of at most 1. So frequency of occurrence of a specific binomial tree having a certain degree is at most 1. What we mean by this statement is that, for example, if we are having a binomial heap, so in this binomial heap, a binomial tree with degree 1 can occur only one time. So if, for example, in the same heap, if I am having two such binomial trees which are having same number of, or which are having equal degree rather, then the second property would be violated and the structure will not be qualified as a binomial heap in that case. So we need to memorize this property, that in a binomial heap, essentially there would only be at most one binomial tree with a specific degree called k. This is one example of binomial heap. So H is the pointer, heap pointer that we have created, for example. Now, as you can see that this heap pointer is pointing to a binomial tree which is having the least degree here. This is a binomial tree with degree 0. Now, this is a binomial tree with degree 2, and this is a binomial tree with degree 3. So as I already have said, the first property says that every binomial tree should be a minimum heap in itself. If we talk about this binomial tree, only one value is there. So this is itself a is a minimum heap here. Now, if I talk about B2, the B2, we can see that on the root node, we are having the minimum value. And if I move forward and go down to the next node, for example, here, this 12 is having value lesser than its child node. So the heap property is satisfied here at every level, and that way we say that B2 is a minimum heap itself. Now, if we talk about the B3, we can see that the same min heap property is satisfied at all the levels, and these binomial trees, they are connected together in a ordered fashion. The second property of binomial heap says that with a specific degree, only one binomial tree can be present. So here we can see that for degree 0, only one binomial tree is present. For degree 1, there is no binomial tree, so that's fine. With degree 2, again only one single binomial tree is there, and with degree 3, again we are having only a single binomial tree here. So the second property is also satisfied here. So therefore, this whole structure is considered as a binomial heap. The operations on binomial heap. So what are the different operations that we can perform over the binomial heap? So for example, the first operation that we have with us is the creation of the binomial heap. Now, how to create the binomial heap? So we already have discussed that for creation, we need to create the binomial trees, and we can combine them together to create the final heap data structure. And again, both of the properties needs to be satisfied for referring to this data structure as a binomial heap. Now, the next important operation is called as the union or the merging of two binomial heaps. So for example, if we are already having two binomial heaps with us, we need to merge them, or we need to find out the union of these two. So how we are going to do that we will see in a moment. The other operation that we can perform is finding out the minimum key out of the heap, that we will be discussing later on. For example, inserting a new node into the binomial heap. So how this operation needs to be performed. Next could be the decreasing of a key. So for example, if there is a certain key present in the binomial heap, and I need to decrease its value, how the heap data structure needs to be maintaining that particular operation, okay, that we will be discussing in this case. Then deletion of a node and extracting the minimum key. So how to extract the minimum value from the binomial heap, that is again this extraction operation that we will be discussing later on. So today we are focusing on the union or the merging operation, how to perform that over two heap structures that are given to us. So to perform the union of two heap structures, first of all we need to combine them together. So the first step is that we need to combine both of the heaps into one single heap data structure. How we are going to do this? So for that we just need to pick up every binomial tree component from one heap, and we are inserting it in order into the first heap. So that way we will be having a merge list of the the given binomial trees. Now what we need to do, that after merging we need to check for these 4 cases. So for the union we are having 4 different cases, and we need to check each one of them, and we need to act accordingly to maintain the binomial heap property for that particular heap data structure. So case 1 says that if the degree of node X is not equal to the degree of node next X, then we need to simply move the pointer ahead. The next case says that if the degree of a binomial tree referred to as X is equal to the degree of the binomial tree which is next to X, and the degree of the binomial tree which is next to X is equal to the degree of its sibling which is next to the next of the X. If this case satisfies, then we are again simply moving the pointer ahead. So these are the first 2 cases. In last 2 cases, what we need to check, that for example, if the current binomial tree is referred to as X, we need to check degree of X, then we need to check the degree of the next binomial tree, and then if these 2 degrees are equal, we are performing the next check. So what is the next check here? That we need to check whether the degree of this next binomial tree of X is not equal to the sibling of the next of X. So if these 2 conditions are satisfied, then in that case the third condition that we need to check is that the key of X should be less than key of next of X. If these 3 conditions are satisfied, then what operation we are going to do? That we are simply removing the next X from the root, and we are attaching it as a left child of the X. Similar is the case 4. If degree of X is equal to degree of next of X, and degree of next of X is not equal to degree of sibling of next X, then we need to perform another check, which is checking over the key values. So we are checking the value of key of X and then key of next X together, and if we find out that the key of X is greater than the next of X key, then in that case we are removing X from the root node and we are attaching it as a left child of the next X. And why we are doing this? So case 3 and case 4 ensures that the min heap property is going to be satisfied. So if you carefully observe here that in this case, when the key of X is lesser, we are keeping it in the binomial heap, and we are removing the next X and making it as a left child of the X node or X binomial tree. Similarly, if the key of next X is lesser, we are keeping that, and in that case we are removing X from the root node and we are attaching it as a left child of the next of X. Now we will see this thing with an example. So for example, this is the 2 binomial heaps that are given to us, and we need to perform the merge or the union operation here. The first operation that we need to perform here is to merge these 2 heaps together. How we are going to do that? We are creating, for example, a pointer heap like this, and I am writing here M to show that this is the merged heap data structure. Now I'm taking it as a reference, and this is the second heap. I'm picking one binomial tree component from here, and in the order I'm inserting here in this first binomial heap. So first there is a binomial tree with degree 0. I'm keeping it like this. B0 value is 12. Then I'm picking up this B0 from here and attaching it like this. So this is again a B0 with value 18. Then after this B1 component I am retaining. So this is B1 with value 7 and 25 here, right? And then there is another B1 component here in this case. So I'm now picking it up, attaching it here. This is 7, this is 3, degrees B1, then 37 here, right? And then the next degree binomial tree is B2. So we are picking up that component from here. 15 comes here, then 28, 33, then we are having 41 here, and this is with degree 2. Now we are performing this and writing this here, this 8, 10, 44, then 30, then 45, and after this 55 for example, and here 20, sorry, here is the 23, right? Now once this merging is done, now we need to check for the binomial heap properties. So the first property says that every binomial tree present here, we can see that every individual binomial tree here is a binomial, is keeping up with the min heap property. The second property says that a binomial tree with a specific degree should only be present at most one time. So this property is going to be violated. So we can see there are two binomial trees with the same tree, with the same degree, again two binomial trees with the same degree. So in that case, we need to perform and apply one of the 4 cases here. How we are going to apply the cases? I will take it as x, I will take it as next x, and this becomes the sibling of next x. Now you need to apply the cases. So first case says that we are comparing this and this. So we are comparing the degrees of x and next x. Both are equal. So case 1 is not applied here. We are again checking degree of x, next x, and sibling of next x. They are equal? No, they are not equal. These two degrees are equal, but this is not. So case 3 or 4 is going to be applied here. Now, once case 3 or 4 satisfies here, we need to check for the keys. So this key is minimum and this is greater than 12. So how we are going to do this? That we are removing it from here and we are making a left child of 12 and keeping this value here. Now the degree is going to be updated and this will become 1. So now we are having 3 components with degree B1 after this operation. Again, we need to start with the same thing and we are comparing each and every case. This becomes x, this becomes next x, and this becomes sibling of next x. Again, the 3 cases we need to perform. Case 2 applies here, which says degree of x, degree of next x, and degree of sibling of next x, they must be equal. So they are equal here. So we are simply moving the pointer ahead and now this becomes x, next of x, and this is the sibling of next of x. So this way, again, we are checking for each and every case, and finally all these binomial trees will be adjusted in such a way so that the second property is going to be satisfied and the final structure will become a binomial heap in this case. So this is all for today. These are some of the references that we have with us, and thank you very much for watching. Thank you.